Alrighty, let's go ahead and get started on the second video of our parametric review. In the last video I sort of reviewed the logic behind parametrics, why they exist, the advantages that they have over just straight up Cartesian XY representations of graphs. And then we actually walk through a couple of examples of graphing parametrics. Graphing parametrics are never really all that difficult if you're actually asked to do them by hand. You just plug in successive values of t into sort of a modified t-chart, just a table of values, plot them, and just show directionality with arrows. In this video, what I would like to do is I would like to deal with eliminating the parameter, meaning going from parametrics to a normal xy Cartesian equation, and of course the other way, going from either a description of a scenario or from the Cartesian, from the xy equation back to parametrics, because both are necessary skills to have. Let's go ahead and let's start off with an easy one. T plus 3 and y is equal to 4t. Now, this ought to be really easy. You shouldn't even have to, deal with eliminating the parameter here. You ought to be able to tell, okay, well, that's 3, 0 as an ordered pair, and the slope is 4, right? Now, if you've forgotten, that's okay, and we'll just deal with it here. Basically, this is x1 plus delta xt over y1 plus delta yt. If there's anything in this sort of format, it's linear. This is the delta y, as in delta y over delta x. This is the delta x, the denominator, right? Because every time in this particular case that the y changes 4, x changes 1, okay? And this will actually wind up bearing itself out. I mean, you have that right here. So you could actually go ahead and say, well, that, you could do formulaically like this, go straight from the parametric straight to point slope form, and then simplify if you need to. Or you can actually do what's called eliminating the parameter, where we actually need to take this right here and solve for t. So if that's the case, then t is equal to x minus 3. You mean this t or this t? The answer is yes. Because those t's are the same, we're then going to take this and substitute it in there, and we're going to get 4 times x minus 3, or y is equal to 4x minus 12. Okay? That is eliminating the parameter. So basically you're going from x and y dependent upon t to just a straight y in terms of x. And that's just basically just straightforward algebra and algebra 2, slope-intercept form of a linear function. Okay? It gets a little more difficult. So if we have something like x is equal to t squared and y is equal to t cubed plus 1. Now with parametrics, when we're eliminating the parameter, we have to be a little bit careful, okay? Because sometimes there are limitations in the domain, or in basically what x and y can be based upon their relationship to t. In this particular case, you know that x is always going to be non-negative, okay? You know it's going to be non-negative because t squared is always 0 or positive, okay? That's not likely to be a problem in this particular one because all you have to do is just transform t into root x, or you could actually, take y and basically rewrite the t cubed like that, okay? Because basically it's just going to wind up being x to the 3/2 plus 1. Okay. Well, here's the thing. If you're square rooting it, then x can't be negative here either. Okay. X can't be negative here because x can't be negative here, and x can't be negative here. because, I mean, the denominator of a 2 makes that basically a square root, okay? So the implied limitation on x that was here actually showed up here, but you still need to be cognizant of it because it doesn't always happen that particular way. Well, let's go ahead and move on to an example where it doesn't happen, and the limitations on a variable that are actually explicit in the parametric, or actually sort of implicit, implied in the parametric, need to be stated explicitly once the parameter has been eliminated. So if we have x is equal to e to the negative 2t, and y is equal to 6e to the 4t, what do I know about both x and y? Well, I know that they're always going to be positive. Those are exponentials, right? And remember that when I'm eliminating the parameter, I don't have to solve for t. I can actually solve for an expression rather than a variable. I know that that's 1 over e to the 2t, and that can actually be e to the 2t is equal to 1 over x. Okay? If that's the case, then y is equal to 6 e to the 2t squared becomes y is equal to 6 1 over x squared. Well, in this particular case, it actually doesn't wind up being a problem, since we should know what that looks like. And we know that 6 over x squared, y is always going to be positive. But we also know that x can't be negative either, so we have to put where x is greater than 0. Okay, so y was taken care of by the form of this function right here. The implied restriction that x had, however, had to be stated explicitly, x is greater than 0. So instead of having both sides of that equation, and that's roughly what 6 over x squared would look like, this part is canceled out because it can't actually be a part of that. Okay, and you can pop it into your calculator and look at the difference between y is equal to 6 over x squared, showing both halves of that, and this, which will only show one half of that. Okay, so remember, when you're limiting the parameter, you need to be a little bit careful about a few of the restrictions based upon the relationship that both x and y have to the parameter and the implied restrictions that are there. So it's almost like implied domain, the whole logic of implied domain applied to parametrics. And so it's that logic that we've dealt with before. You just have to be paying attention to it as you're eliminating the parameter. Now, let's go ahead and let's go the other way. Let's say we have x squared plus y squared is equal to 49. And you're thinking to yourself, okay, how do I do that? Well, let's take a break right there. Remember when we dealt with the one in the last video, we had x 2 sine t and y is equal to 3 cosine t. Well, how do you eliminate the parameter? Now, could I actually solve for t? Oh, I could. And I think I did this for you last year. If you actually do it that way, it's extremely obnoxious. But you do know that sine squared plus cosine squared is equal to 1, don't you? So why don't we take that x equation and solve for sine t, and we get x over 2. And let's take that y and let's solve for the cosine, and cosine t is equal to y over 3. So if sine squared plus cosine squared is equal to 1, then x over 2 squared plus y over 3 squared should be equal to 1. Shouldn't it? And that means that x squared over 4 plus y squared over 9 is equal to 1, or 9x squared plus 4y squared is equal to 36. Okay. Now, of course, this shows it as an ellipse. This is it in polynomial form. Doesn't really matter which. So remembering that, let's go ahead and go back and let's look here, okay? So if I know that that's how we eliminate the parameter when dealing with an ellipse, and of course circle is just a specific form of an ellipse, then I happen to know that x squared plus y squared is equal to 49 can actually be rewritten as x over 7 squared plus y over 7 squared is equal to 1 once I divide both sides by 49 and then simplify each of the ratios using rules of exponents. And therefore x over 7 is equal to sine t or sine theta, whichever you want, is equal to cosine t, and therefore we can have x is equal to 7 sine t, y is equal to 7 cosine t, and that would be a legitimate way to do it. Now, could I have just as easily set x over 7 equal to cosine and y over 7 equal to sine? And the answer is yes. Because you're starting out here in xy Cartesian terms, unless they give you a stipulation as to when the graph needs to be at a particular point, you get to choose, okay? Now, let's go ahead and do another one. Okay, let's say that we're given a line, and let's go through, let's say 2, -1, and -4, 3, or something like that, okay? Now, here's the thing. In order to actually do the parametrics, I know that x is equal to x1 plus delta xt, I've already stated that, and y is equal to y1 plus delta yt, where x1, y1 is actually just any ordered pair, as long as they're not stipulating which one has to be, it has to be when t is equal to 0. x1, y1 is just any point, okay? So for our particular purposes here, let's just call that x1, y1, okay? Now the next thing that I need is I need the slope. Well, that's easy enough. I know that slope is equal to y2 minus y1 over x2 minus x1. So in this particular case, y2 happens to be 3, y1 happens to be -1, x2 happens to be -4, and x1 happens to be 2. So that winds up being 4 over -6, or -2/3, okay? Now, could I use 4 and -6? Yes. Could I use -4 and 6? Yes. Can I use -2 and 3? Yes. Can I use 2 and -3? Yes. It doesn't matter as long as the ratio holds, okay? So actually you have about a dozen different options of actually how to write this one, but it doesn't really matter. Let's just go ahead and call it 2, and let's call delta y is equal to -2 and delta x is equal to 3, okay? So we have 2, which that's x1, plus 3t, and then y is equal to -1 minus 2t, and that is a legitimate way to write that equation in parametric form, okay? Now, what I need you to do is that if you have any further questions on this, of course you can email me. You should have extensive notes on this from pre-cal. We went over this quite extensively. But the purpose of these two videos has been to at least recall some of these categories and these ways of thinking through parametrics back to your mind so that when we actually start applying calculus to it, it's comfortable, okay? So between now and the next video, you may actually want to go back and review your pre-cal notes. Hopefully you've held on to them. And shoot me any emails with any questions that you might have. And the next video, like I said, we'll start with 10.2 and actually taking derivatives and stuff like that. So, bye-bye.